This is the solution video for question 8 from paper 1 of the 2019 TMUA or CTMUA exam. In this question, we're asked to consider a function f. And what we're told about f is that it's between 0 and 1 for all x between 0 and 1 inclusive. Then, we're told we use the Trapezium rule to estimate the integral of f between 0 and 1 with n equal intervals. And we're told this procedure gives an underestimate for the integral. Then we're told we use the same n equal intervals to estimate some different integrals. And we're asked for which of these integrals does this use of the Trapezium rule produce an overestimate. So here, let's look at each integral in turn and see if it produces an under or overestimate. So on the left here, we've sketched a function f such that the Trapezium rule gives an underestimate with n equals 3 here. So we'll just use this to explain our reasoning. So using this, let's look at f of x plus 1 in a. So when we do this, we're essentially vertically translating everything by a. And let's fill in the missing bits because we see that these should go down. So looking at this, we see that if we had an underestimate for f, we've still got an underestimate for f of x plus 1 because the same problems that give us the underestimate still remain when we vertically translate everything up by 1. So returning to our original graph, we know a does not produce an overestimate, so we can ignore a. And now we can proceed on to b. So we wish to scale everything by 2. So we'll scale f of x and we'll correspondingly scale vertically the trapezium. So this being the graph of f of x, this becomes this graph here. And we see, once again, the problems with f of x given an underestimate still remain for 2 f of x. And so we generate an underestimate here also. For c, we're asked to consider something slightly different. We're asked to consider this, the integral of f of x plus 1 between minus 1 and 0. So what does this mean? Well, this simply corresponds to doing this integral between minus 1 and 0. And we see all the problems with the trapeziums remain if we're here or here. And so we're going to also get an underestimate for c, because we get an underestimate for our original f of x when using the Trapezium rule. Similarly, for d, we're looking at the integral between minus 1 and 0 of f of minus x. So this means we reflect this graph in the y-axis. So what does that look like? It looks a little bit like this. And we notice, again, all the problems we had originally with the trapezium as being too small still remain. Us flipping everything doesn't change anything, so we get an underestimate once again. So finally, let's look at E. Now, given A, B, C and D all gave underestimates, we really want E to give an overestimate. So firstly, remember from our working 1 that adding a constant doesn't change anything, so we can literally just consider the integral of minus f of x, or what happens when we add this minus sign. So this is f of x here. So we consider minus f of x, we are transformed to this, where we flipped all our triangles in our graph in its x-axis. And we see if we get an underestimate here, we actually generate an overestimate here, because the modulus of the height of this trapezium in terms of distance being smaller than the graph means that we're underestimating because we're below the x-axis. So we produce an overestimate in E for this reason, because remember, adding by the constant makes no difference. And so our answer is E. This is the integral which is overestimated with our trapezium rule use.